Oh, you're the driver?
Yes.
Okay.
All right. So thank you for the introduction. And it's nice to be here at GAIA, and nice to see so many of you here at the last talk. So Edvin and I were from a consultancy called Egghead, and we have worked together with Trafikverket on a digital inspection of railway tracks, essentially. So we collect quite a lot of data in this project, and that's why we're here today to talk about how to make the most of this data that we're collecting. Our project has been part of sort of a larger project at Trafikverket, and in this larger project, the first year that Trafikverket started using this, they've estimated that they've saved around 240 million crowns, and around 60 million have been attributed to what is done in the project that we have been a part of. So we think that self-supervised learning will play a key role in improving our models further for us to make better assessments. And the outline today of our talk is going to be that I will introduce the project, and then I will also introduce a very specific problem in the project, so you get a sort of understanding of the type of models we're working with, and then I will introduce the data set. And after that, I will then show you how we solve this sort of specific problem that I've introduced before. And I'm going to mention something about new model development that will tie sort of into self-supervised learning, where we will go through a little bit of the history of vision self-supervised learning and the theory behind the DINO method, and then also how we have used it in practice. So Trafikverket, that is the Swedish Transport Administration in English. That's a Swedish government agency, and they are responsible for the long-term planning of or infrastructure planning of rail, road, shipping, and aviation in Sweden. And they also own and construct all the state-owned well, roads and railways. And as you will see, there's quite a bit of railway in Sweden. So we have been part of a unit called Underhåll, or maintenance in English, in a group called Analysfabriken, which are around 20 people spread out over Sweden. And this group, they work with advanced analytics, and the project that we have been involved with is one of several projects that they have. So let's talk about this project that we have been working on. I hope you can see in the middle there's a bunch of red lines that resembles sort of the shape of Sweden. So that is all the railway that we have in Sweden, or at least all the data that Lantmäteriet has about the railway that we have in Sweden. And to do inspection of a railway track, what is commonly done is that people walk in the track area and they do ocular inspection. So they look at every component and they note down the condition of the component. So there's millions of components, and this process, as you can imagine, is sort of slow and expensive. We have around 15,000 kilometers of track in Sweden. It is also another problem is that we have people that are walking near the track area, which is problematic because it is dangerous and it can cause delays. And then we also have the human condition that, or rather human factor, that people don't make the same assessment every time and between people as well. So a few years ago, Trafikverket set out to try to do this digitally. So digital line inspection, and that has been our project. Or, I mean, we have been a part of this project. And when I say a line, I mean has a specific meaning. So it is the railway track between two nodes, and you can think about a node as, say, a railway station can be a node. So if we only look at the line tracks, we have roughly 12,000 kilometers in Sweden. So this is what we have focused on in this project, which is still sort of most of the railway network. But of course, this has a few problems as well. We need to develop models that are going to look at pictures, in this case, so vision models. And we need labels, which can be quite time-consuming to generate. And we again have the human factor coming in. That we're doing all the annotation labeling in our team. And for some problems, it's not very easy sort of to decide on what is say crack, for example, and I'm gonna talk more about that soon. So to start with this project, Trafikverket selected a very specific problem, and that is what I'm calling the DEF sleeper classification here. And DEF here stands for delayed ettringite formation. So that is an internal chemical process that is causing crack formation, typically many years after a sleeper has been installed. So a sleeper is what you can see in the picture here, and also in the below picture, you can see the rail is resting on the sleeper, and this is a crop from our data set. So the problem is that we want to classify sleepers into 3 classes, essentially. A red class, which means that we should probably exchange this sleeper. Yellow, we should keep track of the sleeper. It might develop into a red class in a couple of years. Or green, which is it's completely fine. So what is it that we're looking for here? Well, we're looking for cracks, and they're not very sort of easy to see always. I've tried to mark it in red here. I hope you can sort of see the crack in the top picture. And the bottom picture, you can see it to the left of the fastener, so there. So why are cracks? Why are we looking for these cracks and want to classify sleepers in this way? Well, if in these particular sleepers that are called DEF sleepers, if a crack is visible, it usually means that the crack formation is quite severe inside the sleeper. So if a crack is growing into an area near the fastener, that means that the fastener isn't holding the rail down to the sleeper. So this in itself isn't really a problem, but if this happens in a few consecutive sleepers, it means that the rail can move quite a lot in sort of sideways. So in our project, we have only been interested in classifying individual sleepers and not assessing sort of the dangers that can be caused by having consecutive sleepers being read. So the problem is quite well scoped because we have around 25 million sleepers in Sweden. We know that roughly 3 million are DEF sleepers, and around 30,000 are yellow, and around 3,000 are of this red class. And we know roughly where these sleepers are located in Sweden. So with that said, I also just want to point out in this picture below here that in this particular example, we also have a fastener missing. So this is another type of sort of problem we're interested in looking at. But I'm going to talk about the DEF sleeper classification problem in a few slides. But before that, I will introduce the data set that we have, or rather the data collection first. So the Infranord is the company that is doing the data acquisition. They have 2 trains that are taking pictures, and they drive these trains around 120 to 160 kilometers an hour while taking pictures. And in the middle picture, you can see one of the cameras. That's the green circle. And then in the schematic, you can see a few cameras, but today we only have the 2 cameras that are pointing downwards on the track. So we have 1 camera per rail, and then the image is stitched, or the images are stitched into one image. And the image that you see to the right below there is a crop. So it's not sort of the raw image that we get, and I'm going to show it in the next slide. And Infranord, they have been experimenting a little bit with the data collection. So one issue that we have is that different lighting can cause, for example, if the sun is very low on the sky, it can make well, the left or the right part of the image completely white. So that is a problem for us. So they've been experimenting with the data collection, driving these trains during the night and shining artificial lightning down on the track. And you can see it in the middle picture here, the light rod. But this also means that the data that we get from Infranord might have some distribution shifts that we also need to handle. So, and these then are the raw images that we get. So here's 9 of them. And as I mentioned before, we want to cover 12,000 kilometers of track. And if we do this 5 times a year, we collect around 240 terabytes of data every year. So we have the capacity to collect this amount of data. But today, I think we're collecting around 120 terabytes of data. And the images are quite high resolution, so 4096 by 2048. And every pixel corresponds to 1 millimeter in height and 0.75 millimeter in width at the sleeper level. And as you can see, I mean, our pictures, they're all grayscale. And I mean, in this vast pixel space, we're sort of in a very tiny region of it. I mean, we're just looking from the top down on the tracks in grayscale. But we still have quite a bit of variation. I mean, we have different lighting conditions, different weather, snow, rain. There's many different sleeper types, and I'm going to talk about that soon. We have safety rails. If you look at a bridge, the area down there looks completely different. So there is still a fair bit of variation in this data set. Right, so another interesting part with this data set is that if you stack consecutive images on top of each other, you get the whole track. So you can just scroll through this track. It's a nice feature. So they have viewers where you can just scroll through the whole track. Right. So this, then let's move back into this depth sleeper classification problem. And I'm going to just show you how we solve it. To sort of give you a better understanding of the type of models that we use and what we're sort of what we're going to talk about later with the self-supervised learning stuff, just to give you an understanding of what we're trying to do. So we get the data from Infranord, and we do quality control. That's the first thing we do. We basically look if there's too many white or too many black pixels. And then we do an image downsampling and feed that into our first model, which is a binary classifier. So this model essentially just says if this is a standard track or a non-standard track. We know the depth sleepers are only in standard tracks, so that's what we're interested in here. After this step, we need to do image stitching because sleepers can be cut off at the top or the bottom. So we need to feed in a squared image into our next model, which is a track object detection model. And this model finds, all the components that we have on the track, rail, sleeper, fastener, and other components. And from these essentially bounding boxes, we can do feature extraction from the high resolution images. And we can, for example, look at sleeper orientation, or we can feed that into our third model in this case, which is the crack detection model, which is a semantic segmentation model. So for every pixel we put in, we get an answer if this pixel is a crack or if it isn't a crack. And then from this mask that we get out, with some other features, we do a rather simple classification to classify the sleeper into a green, yellow, or red class then. So what we're working on today is to exchange this binary classifier into a more granular model. So we'd like to be able to do a selection based on the type of sleeper that we have. And I'm going to talk about that for a few minutes. So we have decided that we have roughly 8 types of sleepers. What you see on the top here is a modern concrete sleeper. And then we have an old concrete sleeper, and then we have a wood sleeper. And then we have the safety rail versions of these 3 variants. So where you have an extra rails in the middle. And then we have 2 more types, which is a concrete and a wood switch type. So these 8 classes sort of represent roughly the type of sleepers we have. And I'm talking about sleepers here because we're gonna show later with self-supervised learning how we can sort of do clustering and classification of these. But we're interested in developing this model to be as accurate as possible. We have many sleepers, and one way to do this for us then is to use other types of information. We know that only certain fasteners exist on certain sleepers, so we can use this information to constrain the model. But we can then also use self-supervised learning to sort of have a very good encoder or backbone. So essentially the 3 types of model we're interested in are classification models, object detection models, and semantic segmentation models. And when we develop a model, which we basically, we're developing models in-house. We have a few that we have, or that Trafikverket has bought externally. We have around 10,000 labeled data points for classification models. You can sort of quite quickly label sleepers or images. When we want to develop object detection models or semantic segmentation models, we might have on the order of 1,000 labeled images. But we're collecting between 15 to 30 million images a year, which are mostly sitting unused. So when we develop a model, we're just using a tiny fraction of all the data that we're collecting. So then the key question is if we can learn useful representations for all our tasks from the unlabeled data. So one example would be if we can, for the sleeper classification and say a fastener classification, learn useful representations from the unlabeled data set for sort of both these tasks. And that's what my colleague Edvin will talk about now.
Thank you, Mladen. Yes, so we have all this unlabeled rich data, which basically sits unused for most of the time. So the question here is, can we use the idea of self-supervised learning to learn useful representations of all this data such that it can be used for many different downstream tasks, all of these types of classification and semantic segmentation tasks that we have. And the core idea behind self-supervised learning is that we want to design a task where the data provides its own supervision, so we do not need human labelers, because that is very costly, and this would save us a lot of time and money if we could do this. So the idea is that the model should learn general purpose representations from the structure of the data directly, and ideally these features should transfer to downstream tasks such as sleeper classification or something else. And this is something that is of use in many industries, of course, not only in railway tracks. In medical imaging, you can imagine hospitals having a lot of X-ray images or similar images, millions of scans, which requires expert radiologists to annotate. Remote sensing can take a lot of high image resolution, petabytes per year of spatial and temporal complexity. Manufacturing quality control, where you have a lot of streaming data and you want to identify anomalies or rare defects. And of course, in autonomous driving, where you collect terabytes of data per vehicle per day, and annotating that data, especially if it's 3D, is very expensive. So self-supervised learning in the industry has potentially a lot of use if you can do it correctly. However, self-supervised learning is not very easy, and it of course spans a lot of different data modalities, not just vision, but here we will focus on the vision landscape. And it started, you could say, to begin being useful in 2020 when models such as SimClear and MoCo were released in papers. And the idea of contrastive learning was that you wanted to basically train a deep neural network which embedded similar images close to each other in representation space and pull everything else away from each other. The technique to do this is basically you just take one image and augment it, so you get two views of the same image, so the same semantic meaning in the image, and then you try to embed them mathematically, very intuitive, close to each other in representation space, and then pull it away from everything else in the same batch. However, this comes with a lot of problems. You require a large batch size, and it was quite unstable to train, etc. So more methods came out during the years, and in 2021, self-distillation came out, and the original DINO paper from Meta, where you have basically a student and a teacher network, and you try to distill information from one model into another. And then also masked image modeling came into computer vision in 2022, where you use the same type of idea that already existed in language models pre-ChatGPT, like BERT models, where you masked words in sentences and asked the model to predict the masked word. You basically masked patches of the image and reconstructed the image in order to learn useful representations. And then, of course, maybe the state of the art today, DINO v2. There's already a DINO v3 that has come out since we started this project, but also a meta paper that merges self-distillation with mask modeling. So they basically just engineer the both losses into one, and to get the best of the both worlds, to get a useful self-supervised model that learns useful representations. So let's talk a bit about how DINO works more in depth. So also here, the conceptual mathematical idea is quite intuitive. You take an image and you produce different views of this image, and feed them to this distillation pair of networks, the teacher and the student. The student network is the network that is trained using gradient descent, whereas the teacher is a copy of the student. But the weights are not updated with gradient descent. Instead, the weights of the teacher is just an exponential moving average of the student. So you have this type of moving average to produce stability. And the student then is trained in order to predict the output of the teacher, but it gets different views than the teacher. And that's where the cropping enters. And this means that we do not require any negative pairs. So we don't need as big of a batch size, and we circumvent this problem that contrastive learning and previous methods had. And as mentioned then, the student sees local crops of the image. You have your original image and you produce global crops, which are larger area crops of the image, and then the student gets to see smaller area crops. The larger area crops are fed into the teacher. And then the teacher outputs some type of softmax, which is quite abstract, some semantic, you can think of it as a prototype class, basically. And then the student is trained using cross-entropy to predict the same prototype as the teacher, but with a much harder problem because it gets to see much less of the image. And as mentioned, the teacher is an exponential moving average of the student as we update the student. And this has shown to produce features that have emergence segmentation properties. So the attention maps that you get from this shows that the model is able to detect objects in a very good manner. And it has been shown to produce a lot of features that can be used for a wide variety of downstream tasks without any annotated data. So just an image here to show what goes into the student and teacher models here. So say we have this image of a forest or 2 trees, and you produce 8 or something local crops of the image, which is fed into the student network, and then you have the global crops, which are more global representations of the image, which is fed into the teacher network. And then the student tries to predict what is this type of image. Yep. So why did we want to use DINO? Well, for first, it was the state-of-the-art model at the time, and now we have DINO v3, which basically they add a more, basically in DINO v3, as I understand it, they scale up the model so it becomes much more stable on much larger batch sizes. You can train on even more data, so just bigger it's better, right? But in DINO v2, it's a vision transformer backbone. You have different type of sizes here. We have worked with the base model, which has around 80 million parameters. It has been trained on a curated dataset of 142 natural images. And as mentioned previously, it combines self-distillation with masked image modeling and produces features that work out of the box for a bunch of different computer vision tasks, such as classification, segmentation, retrieval, and depth estimation. And no annotations is needed for this. The frozen features can directly be used. However, DINO V2 was trained on a lot of natural images of dogs and cats and airplanes. So how well does it transfer to the grayscale railway images that Mladen showed us before? And the answer is it worked, but not as good as we hoped. So that's why we developed RailDINO, which is a domain-adapted self-supervised learning for railways. So our approach was quite simple in reality: continue the pre-training of the DINO meta model on Trafikverket's 250 terabytes of unlabeled rail imagery. So we start from the DINO V2 checkpoint, continue the training, and still use no labels. Why do we want this continued pre-training? Well, we could retrain the model from scratch, which we also experimented with, but we noticed that it was a lot unstable, and we got a lot of feature collapse and learned features that didn't quite translate into good performance on classification tasks. So we tried turning a bunch of knobs and realized that, well, if we use the pre-trained model, we could retain the general visual knowledge that it had, but adapt it to the specific domain of rail. And it also goes faster for training this model, of course, because it's pre-trained, so we could train it on only one H100 for 1, 2, or even 3 days to get good results, streaming data from the cloud. And here we see some results then. So we have compared our model to some other types of models on a specific classification task. So the classification task here is sleeper classification. So we have 8 labels, 8 different types of sleepers, and the task for the model is to classify which type of sleeper it is. We are comparing RailDINO with the original DINO weights and also different type of ResNet pre-trained models. We add a linear layer to all of these models and then train using annotated data, only the linear layer. So linear regression on the representations of different models. What we see here first is that if we use 100% of the data, all the data we have on sleepers, which I think is around 8,000, both DINO and RailDINO gets as good as we can on this data set. However, the interesting part here is that with much less data, we are able to, for example, with just 1% of labels, RailDINO matches the ResNet trained on 5 or 10% of the data. So self-supervised learning shines when labels are scarce. We're able to do much more at much less labels. So this has conceptually proved that we can use this model to at least this downstream tasks, and we have shown that we can use it on others as well, to get good results without this costly data annotation. And there are some different metrics you can use to evaluate self-supervised learning models, and we see them here. So the first one here, retrieval mean average precision, is basically a measure of how well can you use this model for, like a search engine. If I prompt the image of a tree sleeper to the model, how likely is it that I will get a visually similar image back? Higher score is better here, and we see RailDINO outperforms the other methods in all of these metrics. Silhouette score shows basically how clear the boundaries between clusters are in embedding space. KNN shows us its K nearest neighbors, so K equals 1 here means it's just a lookup table. So if we look at the closest neighbor, and label the image according to that, what accuracy do we get if we do it like that? And separability ratio is basically a global measure of how well separated the clusters are relative to their internal variance. And these are quite substantial improvements compared to the other models, and we get these without any label data. One interesting thing here to note is that actually the ResNet 50 model beats the original DINO V2 in these self-supervised metrics. And we haven't explored this fully, but we do believe that this could be to the inductive biases of convolutional neural networks. Original DINO V2 is a vision transformer, so it has a tokenizer and views the image in a different way than the way a convolutional neural network does with the local view it has of the image. But here we can see how the representations of the DINO, RailDINO self-supervised models looks like if we project them down to 2 dimensions. So we take an image of this sleeper classification data set, embed it through the model. The model produces a 700-something dimensional vector, which we then use an algorithm called UMAP to project it down to 2 dimension. UMAP tries to preserve the geometry of the embedding space as good as possible, but project it down to fewer dimensions. We use this so we can visualize what the model has learned. And then we overlay the labels, which we have annotated, on this representation space. So here you can see why linear probing works so well. Well, the model has already learned to cluster all of these labels without ever needing to see them. So it has learned the semantics of the image. And this is what makes the model useful for a bunch of different downstream tasks. And one interesting thing to note here is this cluster here. You see that there are some blue, or mostly of them are blue, but you see some red dots in the blue. And you could think that, okay, the model has embedded wrong labels into this cluster. But actually, when we investigated these red dots, the model hadn't done anything wrong. It was actually labels that humans had annotated wrongly. So the model was able to find errors that humans had done. So this suggests we can use this model in order to find human errors and redo the labeling to get even better data later on. So this was on the annotated data that we had. But what happens if we take 100,000 of sleepers of the unannotated data and run it through the model? Then we get this image, which we named World of Sleepers because it almost looks like a map of the world. But this is a UMAP representation again. And then we have overlay, the dots that you see are the colors, is the production model that we have today. So the sleeper classification model that we are using today, what it thinks these labels are. So we see that, okay, we have 8 different labels and different islands, and the model has learned to distinguish between a bunch of different stuff in this space. So we have built this tool where you can click on a dot, and if you click that dot, an image shows up, and you can see what type of image that is. So you can use this as a data exploration tool to investigate data quality and find new training data, etc. For example, this cluster here, if we look at that, I think that is tree sleepers, so sleepers made out of tree. Most of the sleepers in the data sets are concrete sleepers, which are the blue dots. I think light blue is modern concrete, and dark blue is old concrete, so just different type of concrete sleepers, so that's the vast majority. But for example, we could use this model just to find a lot of tree sleepers, which is a class which we don't have that many labels of, and then just populate them and annotate those data points in order to get an even better classification model. And yeah, here we have the concrete model cluster, and we could also use this type of UMAP representation space to find rare defects, rail cracks, or bad data quality clusters. So for example, this cluster down here has only images that looks like this. So it's an island that is different from everything else in the data set. And it is some type of bad data quality island where you have this black bar where a lot of data is gone in the image. So we can find that data easily and just remove it from the training data set if it proves to be of bad quality for the downstream tasks. So what does this mean for our industrial ML pipeline? Before, we spent a lot of time labeling data. Each model was trained from scratch. We had different models or different backbones for each type of problem that we had, if it was semantic segmentation or sleeper classification, etc. And that didn't scale to new use cases, and most of the data sat unused, all that 250 terabyte of data. Now, when we have this self-supervised foundational model, we pre-train one using all the data we have available. We fine-tune only on 1 to 5% of the data for that specific task that we are interested in. This transfers fast to new tasks, and all images from that sits there on the S3 bucket are used for training. So the future outlook regarding this is that in the near term, we want to investigate other self-supervised learning methods. DINO v3 has already come out, and there's a lot of other interesting methods coming out quickly in this research area. We want to use it for better data curation, use this UMAP tool to find bad data, good data, etc., find human errors and fix them. This ties to active learning, so use the embeddings of the self-supervised learning model to guide efficient learning. And we want to evaluate these models on even more. I only showed you the linear classification problem here, but we want to try to evaluate it on semantic segmentation tasks as identifying cracks in sleepers, but also on object detection, like finding fasteners and stuff like that. In medium term, we want to use so-called sequential self-supervised learning, where we leverage the sequential nature of track imagery. So Mladen showed you the long image of tracks. And you could imagine that the previous sleeper could affect the quality of the next sleeper. So you have like this sequential dependence in the data, which you could incorporate in order to make the analysis better. And then long term, looking at multimodal self-supervised learning, incorporating different modalities of data. It could be LiDAR data, thermal data, and track geometry data, together with these images that we have already seen. And yeah, I think that was everything for us. I just want to thank everyone for listening and tuning in today.
Thank you, guys. Excellent, very interesting. My mind is a little blown, actually, when you talk about the word sleepers, because as a child in Sweden, you have obviously encountered the word sleepers, which is something that you use to build sandboxes and stairs in people's gardens and everything. I'd never thought of the similarity with the English word. Okay, I think we have time for a couple of questions, if you're up for it. Good. Did you ever use the fact that all images are almost exactly identical?
Well, sort of, because that's a problem here. A lot of data is redundant, like a lot of it is background, like these stones that you see on the back of the image. So we developed a smart cropping system in training the model. So basically, when we input the model, when we input an image to the model, how do we do that in the best way to preserve as much signal we want? So we know approximately where the rail is in the image, and we know approximately where the sleepers are, so we can do a smart sampling of the image when we feed it into the model in order to receive the signal. But then also, I didn't mention it, there is a third part of the loss function in the DINO model, which is a loss called Coleo loss, which is basically, it forces representations to be far from each other in representation space when training the models, so not everything collapses into the same point. Yeah.
Interesting, thanks. You mentioned this a little bit at the end here, but what's the plan around other technologies? Like you mentioned LiDAR, and I mean, could there be vibrations or sound or things like that?
I mean, currently we're just focused on our data set is these images. I don't know what the plans are like from Trafikverket side, but in this project it's just images, currently at least.
RailDINO was based on DINO version 2 or V2, and DINO V3 is closed source. Have you tried it?
No, we haven't experimented with it yet.
No. What's your reflection on Meta going closed source with their models?
Too bad for us. I love open source. It's better if they do more of that.
Yeah. Okay. You mentioned 98% accuracy, but with such skewed data accuracy doesn't sound very relevant. Precision recall, do you use?
Yeah, in
like
this
that?
data set that we showed here, we actually had a balanced label set.
Yeah.
So the same amount of labels for each class. But yeah.
Yeah, I mean that's
That's
you.
yeah.
Yeah. It's. I mean, I think we'd like to use the UMap that Edvin showed. We'd also like to use that to try to sort of evaluate on a much larger set than just our test set.
Yeah.
And just to clarify on that also, 98% might sound high, but actually we think 98% is low because we have 25 million sleepers. So if we could reduce the error from, like the error rate is 2%, if we can reduce it to 1%, we would half the number of errors, which is a lot when you have that many sleepers.
Yeah.
And also the numbers here look worse than they are because in those 98% test accuracy, a few of those errors are actually not errors, as I showed you on the slide before. If we go way back here, some of the data in the test set is wrongly annotated by humans. So the model is actually better than what we measured.
Okay, yeah. And do you have any additional data apart from the images, like installation year, or who was the manufacturer of the rail, or?
I mean, so I'm not sure this answers the question, but because we're covering the same track multiple times a year and like year after year, they are building a registry of components so they can keep track of like the health of the components. So that's not really the question. But one thing with this sleeper classifier is, I mean, we've only split the concrete sleeper into two categories. So one is modern, so basically by year, and there's, I mean, you could take this further, of course, split them into many more classes, but it gets very tricky to see that visually. And I mean, there isn't a registry now that we know by GPS position this sleeper, you know, was installed this year and it's of this type. But that is all sort of what we're building up with these tools. So hopefully in the future we might have something like this.
Good. Thank you. Super interesting. I do a lot of train travels myself, so I'm going to look at this in a whole different perspective from now. Thank you so much.
Thank you.
Thanks.
And before you go,